most advanced tool in the world. In closing, I would like to thank our administration team and Project Director of ANRF-PAIR, Professor Brahmanandam Manavati, for his support to make this day possible. To our participants, I hope this day marks the beginning of a deeper fascination with analytical science. Let this be a day of learning, networking, and inquiry. I once again welcome you all, and I wish you a very productive and inspiring training session today. Next, I'll call the head of the department, Professor Shamishta Banerjee, to give her remarks. Thank you.
Good morning to all of you once again, and warm welcome. I, on behalf of the Department of Biochemistry as head, welcome you all once again to this one-day workshop on GCMS and HPLC. And as Ajay said, it has been funded by Department of Science and Technology under the scheme of Funds for Improvement of Science and Technology Infrastructure, FIST. I feel proud to say that we have Department of Biochemistry is known for its excellence in teaching and research, and the vision is to continue to maintain high standard of research and innovation, contribute to the knowledge base of the country, and produce human resource with leadership quality. To briefly tell you about the kind of research theme that we work on very fundamental biological question which spans a number of areas. Our research outputs reflects in our publication, and we have published in very high impact journals, and more importantly several of the society journals. We have ongoing projects and new projects that keep coming to our department, indicates the belief faculty of our entire the science funding agencies. As we are currently running DST Phase 3 as well as ANRF-PAIR, and our faculty are involved in leading both the programs. So these are some of the facilities, equipment we have, and several of them are very high-end facilities as they are listed here. It was important for me to show you these, that we have been trying to equip our department with best of the equipment, because all of you would agree with me that science or in our life sciences has become a very technology-oriented science. Particular workshop alliance and chromatographic technique have been instrumental in giving answers to several of very fundamental basic biology question, where you try to understand the biomolecules as such. You separate them from as chemical entity from complex biological system, and then try to figure out what is happening in the context of the biological system. In that context, I feel that this one-day workshop on HPLC and GCMS should be very, very useful for all of you. The program has been very appropriately chalked out, and I see there are first kind of lectures which will give you the theoretical background, followed by demonstration. I think one important thing that we expect that would come out of this is not only to understand that what we see as result, but I think to understand what we see is not a result. And with this, I, on behalf of, once again, the department, I wish you all a very fruitful day ahead. Thank you so much.
So today, the workshop is about the technology again. You have HPLC and GCMS. These are the technologies which is going to be very helpful for your career. Not only for your career, but also definitely will be useful for your research activities as well. So I take this opportunity to introduce that ANRF-PAIR. University of Hyderabad is one of the proud recipient of this grant, Anusandhan National Research Foundation, which is by a special act of Parliament. It was introduced in 2023 August by Government of India. The primarily to promote the research in India. Okay, it was earlier it was there in the SERB, but now it has been replaced by the ANRF. So one of the flagship programs of the ANRF is PAIR. What is PAIR? Partnerships for Accelerated Innovation and Research. Simply call it as a PAIR. So PAIR mandatory is to support the research where it is actually lacking the proper ecosystem, like state universities where the ecosystem is very poor research ecosystem. So try to build the ecosystem. Then who are going to help them to build the ecosystem? So the responsibility is lies on the higher organizations, like institutions like IITs, central universities, and NITs. So who should play a major role to handhold these spoke institutions? We call it as spokes, because they introduced this concept called hub and spoke. Hub means they have actually categorized the institutions across the country into three. Tier 1 institutions called as hubs, because these are the institutions demonstrated scientifically and academically very well. So therefore, they are the leaders. Okay, they can be act as a mentors. Okay, so University of Hyderabad is one such mentor, and we have actually taken like 6 spoke universities. Spokes comes under the category 2, where the research is very poor, even though they have the capabilities, but unfortunately due to lack of infrastructure, or maybe due to lack of the proper drive because of the research drive. So you need to promote them. So therefore, a kind of good research ecosystem will be established across the country. So this is the primary objective. University of Osmania University, Mahatma Gandhi University, Yogavemana University, Kannur University, and Central University of Karnataka, and Yogavemana University. So these are the 6 universities have been identified as the spokes. We have altogether 173 faculty members and 173 research fellows. We call them as PAIR fellows. Okay, 30,000 rupees per month as a kind of consolidated fellowship, and so the total grant is about 100 crores, and it is 30:70 ratio. So the hub will take 30%, and 70% will be taken by the spokes. Okay, so one of the important deliverables, the core theme of the entire project is innovations in healthcare and medical technologies, sustainable health for a resilient future. There's a beautiful title, resilient future. The resilient future, why we kept this is, there are several bottlenecks in the field, in the country, like an accessibility, particularly in the case of healthcare industry. We have accessibility is a problem, affordability is a problem, and also sustainability is also a problem. So therefore, combining this, all these three to overcome these important limitations that what we are facing in the country. So we took this challenge, and proposing 3 important ideas in 3 different diseases. Okay, one is the metabolic diseases. So where we considered fatty liver and diabetes, and in the case of infectious diseases, we considered malaria and dengue, and in the last cancers, breast and blood cancers. These are all some of the very relevant and pertinent to the country. Okay, that the metabolic disease, particularly the diabetes, is India is a capital for the diabetes disease, right? So the overall the deliverables of this project is to provide the affordable healthcare technologies to the country for the to meet the the next generation the people. Okay, so with this brief idea, and then thought about this the PAIR grant, I hope that this one-day workshop will be certainly a wonderful opportunity for you. Use this technology, okay, and learn as much as possible. And we have 2 eminent scientists are here, Dr. Santosh and Dr. Ajay, who are going to be definitely helpful to you to enrich your knowledge in the field of this equipment analysis. Okay, so once again, I welcome you to the University of Hyderabad, and then I wish you all success for your this one-day workshop. Thank you so much.
Thanks, Professor Brahmanandam. Now, I'd like to call upon Professor Santosh Padhi, who is also the person who is organizing this, and He has done a lot of hard work behind putting this whole program. I call him to provide the vote of thanks for this particular session.
It gives me immense pleasure to give vote of thanks on today's occasion. First of all, on behalf of the department, I would like to sincerely thank the Dean of our school who could not make it, but Professor Anand Sir, for kindly facilitating this event. His constant support was instrumental in making this event successful. On behalf of the entire department of biochemistry, I would like to sincerely thank three stalwarts of our department: Professor Sarmishta Banerjee, head of the Department of Biochemistry; Professor Brahmananda Manavati, the project director of ANRF-PAIR; and Professor Naresh Babu Sepuri, the principal investigator of DST FIST, who are instrumental in giving realization of this event, this one-day event, one-day lecture cum demonstration of GCMS and HPLC based analysis. Our profound thanks to Professor Ajay W. Tumhane for leading this program and ensuring that the event runs magnificently. He left no stone unturned to make every operational successful. We are very much thankful to you, sir, for all his wonderful efforts. I thank Dr. Anil for his help in organizing this event. We are thankful to the staff of the Dean's Office, Biochemistry Office, student volunteers who are instrumental, and others in the school for their support in smoothly organizing this event. Finally, I thank you all the audience, for your patience and coming all the way from different parts of the country to attend this wonderful one-day seminar demonstration. Thank you all.
Not like from there you can start. Just introduce yourself, your name, where you come from, and what you are doing right now.
Good morning, everyone. I am Jahnavi. I am from Bicus Therapeutics, which is located at ANRF-PAIR Bionest. So I am from Cell Culture Department, and my department mainly focus on biosimilars. So I have joined this workshop to know more about the HPLC.
Hello everyone, my name is Shivangi Pooja and I am from Ranchi, Jharkhand. I did my masters in biotechnology from Guru Nanak Dev University, Amritsar, and currently I am looking for projects and opportunities, and this is one of the biggest opportunity for me to interact and to know so many things about the analytical techniques. So this is one of my biggest opportunity to be here and to interact with you all. Thank you.
Nice to know you have a different objective, but that still fulfills, I think. Yeah.
Hi, I am Sudhir. I completed my MSc in Genetics and Genomics in Yogavamna University. And now I am working in IAMR. I want to learn more in HPLC, that's why. Thank you.
Very good. Yeah.
Respected faculty members and the participant, good morning to one and all. I am L. Pawan Kalyan from Yogavamna University, Kadapa, and currently I am a project associate member in PAIR project. I just want to know more about GCMS and HPLC, that's why I am here. Thanks for this opportunity. Thank you.
Good morning, I am Gaurav from Bhavan Vivekanand College. I am right now pursuing MSc in microbiology. I am here to know about HPLC, how it well done. I am interested to hands-on experience with this.
Definitely you will. Yeah.
Good morning to everyone. Myself C.H. Vamshi from Bhavan Vivekananda College from Department of Microbiology. I'm here to experience how HPLC works and how GCMS works.
Very good.
Good morning, one and all. I am Maunika Vemgal. I am a recent master graduate from Osmania University in Biotechnology and also a recent intern at Denome Private Limited, which is incubated in the Bionest. So yeah, today I came here to learn more about the GCMS, which I'm very much interested to know about the mass spec and all. Thank you.
Good morning everyone. I'm Nagayoshna, pursuing MSc Biochemistry from Mahatma Gandhi University from Nalgonda. We have learned HPLC and GCMSC as theoretical, not experience practical, so it will be best opportunity to know it. Thank you.
Yeah. Good morning everyone. I am Ranjit and currently I am working as a JRF at Madras University, and currently also I was selected at ISER Berhampur for my PhD, and there they were working, my topic is like on metabolites of sea grasses to characterization, so that's what I came to attend this. Thank you.
Hi, I'm Hadia. I did my master's from MES KVM College, University of Calicut. And it is my first experience on GCMS and HPLC.
Hello, my name is Sri Lakshmi Santosh. I'm a final year master student from Vellore Institute of Technology. As they said, I've also only dealt with the theoretical aspects of HPLC and GCMS, so hopefully I'm hoping to get practical insights on this. Thank you.
Good morning, everyone. Myself, Deeptishika. I'm from Hyderabad, Gokaraj Rangaraju College of Pharmacy. Currently I'm doing M-Pharmacy, Pharmacology Department final year. I was interested and curious to learn HPLC and GCMS, so I was here. Thank you for this opportunity.
Good morning to everyone. This is Ramya from Mahatma Gandhi University, Nalgonda. We are interested to learning in practically GCMS and HPLC. So we attend here. Thank you for this opportunity.
Good morning everyone. I am Shweta from Mahatma Gandhi University, Nalgonda. Presently I am pursuing my Masters in Biochemistry. Today I came here to learn more about HPLC and GCMS code. Thank you.
And it's time for lecture for GCMS by Professor Ajay Tumane sir from the Department of Biochemistry. Sir, please welcome.
Yeah, morning everyone. Now we get into this session where we are going to talk about the two equipments, the GCMS and HPLC, what we are going to have the demonstration today. So what I'm going to do today is just to give you very basics about GC and followed by GCMS and what are different components, how those components are useful, and what are various things under those components which are there. This will help you when you go to the for the demonstration, and we see when they talk about all the different parts and stuff like that. At least it will be useful for you to understand what they're talking about. So to start with, what you can expect today is we'll just start with chromatography because we are talking about gas chromatography, mass spectrometry. So we'll first talk about chromatography just to brush up our basics because that will set the ball rolling, and then we talk about gas chromatography, various components of it, what you're going to see when you see the machine, what are different components, what are there. Then we'll talk about mass spectrometry, GCMS components and working, and then some applications of what GCMS can be used for. So I'm sure this is a basic knowledge which is there from maybe bachelor's days or maybe even before that. What is chromatography? So it is different substances are partitioned between two phases. So if you have two different phases, generally we talk about solute and solvents. In those two different phases, there is a solubility of any particular compound, right? And depending on the affinity of this particular compound against those two phases, there will be difference in terms of how long they can be absorbed on that phase. So you have one, generally in chromatography, you have one stationary phase which is stationary, another one is a mobile phase, right? These two phases, your particular compound which you are trying to analyze will have affinity towards these two phases in terms of solubility, whether it's soluble more in your stationary phase or more in the mobile phase. Depending on that, there will be differences in the solubility, and whatever you're trying to separate will have different mobility in that, right? So that's why you get different separation on these two different phases. So you have stationary phase and mobile phase. So what you can do, which are the components which are there in a particular mixture because of their whatever solubility in the two phases, and how much of them are present. So if this particular kind of principle is there in any technique, then it's easier for us to separate various compounds in a particular mixture because they'll have different properties in these two things, right? So in terms of separation principle, in GC you have between mobile phase, solid phase and liquid stationary phase, polarity of compound is what is important in terms of separation. Boiling point of compound is important. In terms of LC, you have liquid stationary and mobile phase. Again, here also polarity of compound is important. Separation mode can be of different modes, where you have ion exchange chromatography in LC, size exclusion chromatography, or reverse phase chromatography, right? Mobile phase, that's what the difference is all about. When we talk about GC, it is gas, inert gas, and when we talk about LC, it is liquid, either it's in form of a solvent or a buffer, right? Pressure requirement requires lower pressure to operate, not really much is needed here, but in terms of HPLC, when we call it as high performance or high pressure, it requires high pressure to operate, right? Sample requirement, important thing is volatility, because your mobile phase is gaseous, your compounds has to be volatile so that they can move with the gas, right? They should be thermally stable, because now that you are going to have higher temperatures so that the compounds can become volatile, the compound should be stable at higher temperature. That's very important. And they can be lower molecular weights are better, like alcohols, fatty acids, pesticides, and volatile carbon compounds, right? In terms of LC, they should be soluble in liquid phase. Whatever compounds you are trying to really separate should be soluble in liquid phase, not limited by molecular weight or polarity, because you can do proteins, peptides, amino acid, polymers. You have size exclusion chromatography. Depending on what kind of principle you're using, maybe ion exchange, there you really don't, you're not really limited by the molecular weight. Detectors, most of the time it will be ionization or conductivity detectors, and MS is one of the detectors which is the gold standard and which can be used for GC. And you have like flame ionization, thermal conductivity. We are going to see about detectors in details when we talk about the components of GC. The detection is generally destructive in nature. That means that the compounds which are coming out when they are being detected, they are most of the time they are destructed. Here you have various detectors here. You have UV, fluorescence, refractive index detectors, conductivity and light scattering detectors. Most of the time it is not destructive, non-destructive. So in LC, this is one of the advantages, where your compounds which are separated can come out and can be utilized for further analysis, because they are not destructive in nature. So to talk about GC in a little bit of more details, like we said, separation of volatile organic compounds. These should be volatile when heated, and they undergo phase transition into intact gas phase species. Now, many of your compounds which you're trying to separate may not be volatile in nature. So what you have to do is you have to make them volatile by derivatizing them. So when you derivatize any particular compound, you can use derivatization, which can make that compound more volatile at higher temperature versus the original intact native compound. So you have to do derivatization. That is one more prerequisite of GC for few samples which are not really volatile at higher temperature. The separation occurs as a result of unique equilibrium between solute and the stationary phase, that is the GC column. We'll talk about columns also. And the inert carrier gas carries the solute through the column. So you have a column through which, that is the stationary phase, gas is the mobile phase, and the gas is inert. It carries the compounds which are to be separated, and it separates on a particular column. So if you see, that's the stationary phase of the column which we're talking about. And then you have a carrier gas, which is a mobile phase. This is a sample which has different molecules which are there, different compounds which are there in this particular sample. So as the time goes, when the gas moves through this column along with your compound to be separated, the sample interacts with stationary phase, and mobile phase carries them through here. And then you can see that there is separation of different compounds from this particular mixture based on whatever we discussed in terms of principle of how much they can be absorbed depending on their diffusion coefficient. And then the first sample which compound really elutes comes out, and then it is detected as a peak in a particular detector. So this compound comes out, detector detects this compound, and you get a result as a peak for representing this particular compound. That's how the GC works, right? Now, having understood all these things, we'll see what are the different instruments component for this particular GC, which you are going to go and see there, right? So first is you have a carrier gas, which is a gas cylinder. This carrier gas will be different. We'll see in the next slide what all are there. And then there is a flow regulator for the gas, because you can really regulate the flow of how much gas is going to pass through the column. From here, the gas is going to go here, and then it is going to go to the column. But before it goes to the column, the sample has to be injected before the column, right? So then you have an injection port through which you are going to inject the sample, and this injection port is also important. We'll see the details of it. And then it goes into the column, and column is placed inside an oven, because we need higher temperature for GC. So this oven is there which is thermally controlled oven, and you can control the temperature, you can set a temperature, you can set a temperature gradient, that over the time you want to increase the temperature, decrease the temperature, or keep the temperature constant. So this oven is important here to make sure that this whole thing is moving and gas is moving. And this is the column, and then you have, once the gas comes out, your compound which is injected comes out, it goes into the detector, and the detector will give the signal, which will be, output will be in terms of peaks on a computer or a graphic which you have. So this is the whole how GC looks like. So these are, like we discussed, these are the various components which are there, and we'll try to see some of the important ones, what they really mean. So the gas is the most important part. We have already discussed about it, that it's the mobile phase, and it has to be really pure, because if your gas is not pure, then whatever you're trying to detect in the impurity of the gas will also be detected, and then you'll have a mixed result which is not really good for you, right? So you have a compressed gas, you have a regulator, and then you have some traps which are going to trap all the impurities in the gas, right? You're going to see that there, that there'll be traps which will be on the wall mounted from the cylinder. When the gas comes through the pipe, it'll go through this, and the purified gas is going to come out, right? The gas should be free from moisture, organic hydrocarbons, and oxygen. So this is the prerequisite for the gas, and this should be free from components those associate or interfere with the analysis. Recommended at least 99.995% purity of the gas should be there. I mean, if you go to that purity, you get the gases which are of different grades. You can get 99% pure gas, but if you go for higher purity, the gas becomes more costlier. But more the pure the gas is, more clean your result will be, more clean your data will be, which can be really accepted, right? And purified traps must be installed to get the right kind of gas purity inside. So most commonly used gases are hydrogen, helium, and nitrogen. And these are the pros and cons of it, based on which you can use it. So carrier gas can be any of this. Hydrogen is used most of the time because of high diffusivity and linear velocity, because it just gives the linear velocity. We'll see what it means. It gets good separation efficiencies, the separation of the peaks, the compounds which are there, they are better with hydrogen. Short analysis and runtime. So hydrogen, it moves really fast, and you can have short analysis and shorter runtime. Cons is hydrogen is flammable. You have to be very careful about it, because it can really catch fire very fast, and not completely inert, because it can react with some compounds at higher temperature. So this we have to keep in mind when we are trying to choose hydrogen as a carrier gas. Helium, inert, non-flammable, gives high resolution, but it is expensive and not easily available. So you might have to pay more money for it, and it's not easily available. Nitrogen, as we know, nitrogen gas is available and it's cheap, easily available, but at times it's not suited for temperature program GC analysis, lower pore separation, long analysis, and runtime. So depending on what kind of analysis you're doing and what kind of running cost you have with you, what you can afford as gas, you can use that, but you have to keep these pros and cons in mind when you're trying to use these gases. So once we talk about gas, now we are going to move about the injectors through which we inject the sample inside the GC, right? So it's the area in which sample is introduced, evaporated instantaneously, and carried to the column with a minimum load of spreading. So generally a typical injector looks like this, where you have a septum here through which you, through the injector, you inject your sample here. And the injector also has a temperature gradient in terms of the depth. But so wherever your needle of this, your syringe goes inside, you can see that around the injection port is there will be around 280-300 degrees will be the temperature where it goes. And this is important because most of the time your sample, as in this case, is in liquid form. And we want that liquid form to be converted to gaseous form, because gas is the carrier mobile thing. So as soon as you inject your liquid sample inside the injector, the temperature is so high that it becomes gaseous in nature, and then it can be taken from here inside the column, right? So, so around 280 degrees or more has to be the temperature of this particular injector. And then there are various purge wall control are there, which will allow whether how much sample should go inside the column or not. Yes. So you can't inject solid samples in your GC, right? It has to be in liquid form, because that's how we can inject inside the injector, right? So if solid sample is there, either you try to dissolve them in some solvent or whatever you want to derivatize them, but it has to be in liquid form. Then only it can be transported into inside as a gaseous phase, right? Yeah. So when we inject the sample inside the GC, there are various ways in which you can inject, depending on different things what you're trying to do, right? So you'll hear this term whenever you see the protocol or methodology or materials and methods where GC is used. People will talk about spitless, split, or direct on-column injection, right? So what does that mean? So you have a split injection is where this is the gas which is going through here, and this is the opening for the column. There is a split vent which is here, which can be opened or closed, right? So if you open this split vent, the gas can go from here, and your whatever the compound which you're trying to also identify or trying to separate can also move out from here, and some part of it will go to column. If you have splitless injection, then you close this vent, and then all whatever sample you have injected has to go inside the column, right? And then this is direct on column injection which is done. So why we do all this? Split injection, as it says that some of it will be go outside, because if you have high concentration of your analyte, what you're trying to analyze in your sample, and you don't want to overload the column with all whatever you've injected, then you can remove most part of it, and then you can put only small amount of that analyte inside the column. So this is called split mode, right? And the split ratio can be at different ratios. You can set it to 1:99, 1:100, 10:99, depending on what kind of concentration you think your compounds are in your sample. If it is more concentrated, then you can have the ratio as 1:100 or 1:99. Yes.
Which we don't know what exactly it is, that will be a mixture of samples. So we have to just heat and trial method to standardize the process, or?
So when you are trying to extract or isolate the sample, I mean, you'll have the idea saying that you are taking microgram, milligram, right? And in a particular volume you will have. So generally, if you are trying to do any analysis on GC, it's better to have less than microgram quantity of the sample with which you are analyzing. So based on that, you can initially try it, but then it's better to do with the lower 1:10 split, and then once you see that it's more, then you can go for a lesser amount of sample. So the split ratio can be changed. So it's just to make sure that only small portion of sample is going inside the column, and to avoid overloading the column and unresolvable peak, because column is very small, delicate, and if you put a lot of your sample in it, it'll get contaminated, and most of it will be stick to it, and then your subsequent runs will have your previous sample whatever was there. So you try to make sure you do less. In terms of trace analytes, you know that these analytes are in very nanogram quantities or picogram quantities, and there are volatiles, residual matrices are there. For that, you can introduce the whole thing. You close this split vent, and then the whole thing can go inside, and then it can give you accurate determination saying that total whatever I have isolated has gone inside the column, and I can directly find out how much of that is there. In terms of on column or direct spotting, you have thermally labile low volatile or reactive analytes. So generally it doesn't go into the hot injection port and goes directly to GC. So there are some certain compounds which you really don't want to put them in your high injection temperature port, which is 280, 300, because those are gases, but then they can get thermolabile, so they can be destructed. So then you directly put them on the column directly without going through this, and then it can be called on column or direct injection. So the machine what we have, Agilent GCMS, we have all these three options there. We have split, splitless, and also on the on column direct thing, so that we can directly check things which are heat labile, right? So once we inject the samples, now the samples are going to go to the column. So how do you select the column, right? At times we have that the question which we have, and I mean there are various columns which are available now. Various makes are there, and if you really put, you know what kind of nature of your compound is, what kind of nature of your analyte is, you can use a particular matrix for that. But the rule is the non-polar component is dissolved in a non-polar liquid phase. The polar component is dissolved in polar liquid phase. So that has to be the rule when you're trying to see what kind of stationary phase you're using. Elution order of interest component versus matrix. What is the matrix and elution order? You should have a little bit of understanding of how this works. Resolution of a column, separation capability, how much it can separate, and temperature limitation of stationary phase, because the stationary phase, whatever is inside, is made up of certain compounds which might have some temperature limitations, and if higher temperature might harm that. So if you look inside the column, there are, you can say, 3 different kinds. So you have stationary liquid phase, which is here, you can see, and you have it's called WCOT, wall coated open tubular. You might hear this term, or when you look for a column, you might see that this term is there. So it means wall coated open tubular. Then you have solid support coated with liquid stationary phase. So you have a coating of solid support, and stationary phase is liquid. And then it's called SCOT, super coated open tubular, and then you have stationary phase solid particles. So it's called porous layer open tubular. So these are 3 different kinds. You can classify this columns into depending on what kind of stationary phase it has, either liquid, solid, or liquid solid support phase, right? So polar versus non-polar column. Separation is based on vapor pressure and polarity of compound. You know that what is the compounds which you have, which your polarity of this compound. So within a homogeneous series, like you have series of alkanes, alcohols, fatty acids, retention time increases with chain length or molecular weight. So this kind of principle is applied, and when you see any chromatogram, let's say you have a mixture of fatty acids, then you can see that with the shorter chain fatty acid will come first, and then the longer chain will come later. But that doesn't hold true always for the unsaturation, saturation in the chain. But then in terms of chain length and molecular weight, that's how it works, right? Polar column retains polar compounds to greater extent than non-polar column. So you should remember that what kind of polarity is there for your column, and what kind of polarity is there for your compound. So if you look at this particular example, so if you have a polar column, then you have C16, C16, these are the fatty acid, palmitic and palmitoleic acid. You have 18, 18, 18, that is stearic, oleic, and linoleic acid. You can see on polar column, they are going as per their chain length. So 16s are here, 18s are here, and then you have double bonds, so they are going further. But then if you take non-polar column, then you will see that the double bonds, the unsaturated fatty acid is coming before the saturated fatty acid, right? So this separation, if you know, then you'll see that once you inject this kind of samples, where these are expected and where they can come, and accordingly you can use your columns, right? So these are some of the column materials, the stationary phase, which are available. I'm just listing some of them, and depending on what kind of polarity you need, non-polar, less polar, mid-polar, polar, you have different matrices which are there, the stationary phases, and this combinations will give you either polarity or non-polarity, what you're looking for. So polarity increases with whatever we are looking at here, and depending on what is your nature of your compound, what you're trying to separate, based on this, you can use either of these columns and go ahead with your analysis. So the GC columns also come in basically 2 different kind of classification you can have. So it's like packed column and capillary column, right? So this can be packed, which are already packed inside, and a capillary open tubular will be there. And we saw this WCOT plot and SCOT. But in packed column, you have porous solid or liquid coated solid. So these 2 nomenclature you will keep saying that it's a packed column or it's a capillary column which was used. So this is what these things mean, right? So the column, now we move to the oven, because column is placed in the oven, and it can be programmed. So you have an isothermal run where you run at one constant temperature. So you set a particular temperature for a column and say, I want to run the whole thing at a particular temperature. That can be done. And then you can also have a temperature programming where you start with low temperature and gradually ramp up the temperature of the oven, so and in turn the column, so that you get more constant peak width, better sensitivity for component that are written longer, much better chromatographic resolution, peak refocusing at the head of the column. So when you change the temperature, then you will see that versus isothermal temperature versus temperature programming, you can see that there is better separation because of this temperature, whatever changes we have. So to just show you one particular example, here we are seeing that this is isothermal separation of a particular mixture. At 70 degrees, you can see there are 3 peaks which are shown here. But then if you increase the temperature, it's constant, increasing, then constant, increasing, then constant. If you do the different kind of a temperature programming, then you can see that the same sample what was there now is giving you almost 5 peaks. And these peaks are coming between this particular thing which was not really resolved when there was isothermal 70 degrees. You can see that this is a very broad peak, there is a shoulder, but with temperature programming you can see that this and this have come out as a particular peak. So that's the difference between isothermal. It'll give you peaks and then slowly the compounds are not coming out. They are broad peak and shoulders, but once you increase the temperature further or program it, then those compounds also can come as a proper peak and you can attain the separation, right? So this is the importance of oven temperature and how we can use the resolution for that. So from here now we'll move to the injected analyte is now gone to the column, and now it is just going to move out of the column and get into the detector. They are used to determine the presence of quantity of analyte in a mixture, how much of them is there and what is present. Retention time is used to identify the compound. So whatever we saw the peaks, those peaks will tell you the retention time. So that peak is coming at a particular time once you start the run. So let's say first peak is coming at 3 minutes, second peak is coming after 5 minutes after injected. So that is the retention time for that particular peak, right? So that particular peak or that particular compound has a retention time which will be unique and in a particular experimental setup, which is if you have standardized it. Peak area or height corresponds to amount of compound present in the sample. So whatever peak area or height you see, the bigger the peak, the more the compound is coming out, or more the concentration is there. Or in terms of area under the peak, you can quantify that, calibrate that, and find out how much of the compound is there. Ideal detector should be highly sensitive, not affected by variations. It should show linearity. We'll see what linearity means. It should be able to identify and quantify the compounds what you're looking for. Should be non-destructive, fast, stable, and easy to use. So these are the good features of if ideal detector is there. This should be the features you should look for. So like I said, you'll see a chromatogram which is like this. So this is the peak intensity and this is the time. Once you inject here, this is a 0 time, and after whatever run time is there, you'll see peaks at regular intervals or whatever intervals they are coming, right? So this is retention time what we're talking about. So each peak represents a particular compound, and this particular compound can be, like we said, can be identified and can be quantified based on the height of the peak or area under the peak. Now quantification of this particular peak can be done by using a calibration curve. So let's say you're trying to find out a particular compound in a mixture. So if you're trying to find out a particular fatty acid in a mixture, let's say you're trying to find out a 18-0 stearic acid in a mixture. Now what you'll do, you'll inject standard stearic acid of known concentration at increasing concentrations, varying concentrations. So same compound you're injecting, let's say 5 micromolar, 5 microgram, 10 microgram, like that, and you will get a response for that particular concentration. So as the concentration of your standard increases, the peak size will also increase, and the area under peak will be equivalent to whatever concentration you have injected inside. And based on that, you can make a calibration curve. With this calibration curve, you can plot a linearity graph, and this linearity graph is going to give you unknown. If you have unknown sample where you are trying to find out that particular compound, you can just plot it here, and then you can find what is the concentration of that unknown compound. So you have to have a linear calibration curve made for anything which you're trying to identify, and then unknown can be known in terms of the known concentration, whatever is there, by this particular linearity graph, which you can plot by using different concentration of known standard. You have various types of detectors. So you have FID, which is flame ionization detector, which is most common in GC, and the GC what we have, GCMS, also has a FID detector. You have thermal conductivity detector, electron capture detector, nitrogen phosphorus detector, pulse discharge detector, and so on. So all the detectors are used for different purposes, different things. And gold standard one is mass spectrometry, because mass spectrometry is very easy, and you really don't need any standard, because the mass spec is going to tell you what is the mass of the compound which is coming out, and the spectrum is going to tell you what kind of compound is that. So you can really identify that by your mass spectrum. But for others, you might need to have a standard which is there, and you have to make sure that you make a calibration curve for particular that thing, and then you can use it. So these detectors are having different sensitivities, and range is there for various things. So just this is showing that which detector has what kind of range and sensitivity. This is in terms of ppb, ppt, or femtogram, picogram, nanogram, milligram, microgram. So generally FID, which is most of the time which is used, it can go from milligrams to some picograms quantities, but there are certain more like NPT detector which will go towards even femtogram also. Depending on what kind of compound you're looking for, what kind of sensitivity you want, you can choose your detector and you can utilize them. These detectors can be used for, these are various samples, environmental samples, food safety samples, petrochemicals, toxicological samples, and these are various protocols which can be used, which uses this particular detector. And we won't go into details because a lot of things are there, but it's good to know that different aspects of samples from different areas can have different detectors and can be used for seeing this for the analytes what we are trying to detect. So I said that out of all these detectors, then you have the gold standard of MS, and that's what today we are going to focus on, GCMS, right? So if you see GCFID, if you look at this particular peak, it cannot be easily identified or determined, because you need to have a standard for that. Unless until you have a standard detention time for a particular compound, you won't be able to really determine it. But then if you use a GCMS, then qualitative analysis is based on the mass spectra displayed. So once this peak goes to the MS, it will give the mass spectra. That mass spectra is a fingerprint for that particular compound, and from library you can identify that, and you can directly tell which is this particular compound all about. So that's the difference, and that's why you try to use GCMS over GCFID if you want to really find out what the compound is. So a little bit about mass spectroscopy. So its basis of it is production of ions that are subsequently separated or filtered according to mass to charge ratio and are detected. So you have any particular compound, you're just going to convert that compound into ion forms, and those ions are separated and are filtered according to how much charge is there and what is the mass there. So mass to charge ratio is what is going to separate the ions for a particular compound. The resultant mass spectra is a plot of relative abundance of the produced ion and function of mass to charge ratio. So you have a spectrum which has abundance of this particular ion which is formed, and the m/z ratio, that is mass to charge ratio, which is there. That's what the spectra you are going to see. We are going to see some spectra later, so that will make you understand this better. What it gives us information, it gives us molecular weight of a particular compound, whatever has been separated, elemental composition you can get at times, and structural information also you can get if you're using right kind of ionization method. So the mass spectrometer has a sample inlet. In our case, it will be from a GC, whatever the sample is separated in GC, it's going to go to the MS. If you're using this as a detector, so this is the GC sample which is coming inside. Then, as we said, that you have to ionize whatever is coming inside the mass spectrometer. There is been one ionization method which will ionize that. there'll be mass analyzer, which will analyze the mass, and then there'll be detector for this, and then you have data which is generated. So if you're looking at here, down here, you have this sample inlet from which various compounds are getting inside. There's a lens stack here, and which is going to make sure that your ionization method is placed here, you're ionizing things. Then here what we are seeing is quadrupole mass filter. This is a quadrupole mass filter where you have 4 rods which are at different charges, opposite charges against each other, and here the ions will move from here, and then they are going to go to the detector, and then they are going to go to data system. So here what you're going to see is a mass spectrum of a compound which is coming out. We'll go into details, you'll understand better, right? So how do we do ionization? Ionization can be done by electron ionization, it's called EI, or chemical ionization, it's called CI, right? So in electron ionization, which is mostly we use, and our GCMS what we have also has EI, you have this particular compound which is there. This particular compound is ionized using electrons, beam of electrons which are put on this. This will create an ion, which is, because this electron will bombard with this, and couple of electrons will come out, and this positive ion will be formed for this particular M. And then that will be fragmented in F1, F2, F3, or various kinds of fragments. So this particular process, the importance of here is that at 70 electron EV electron beam, any particular compound will have a same pattern every time, right? That's the beauty of this. So if you take any compound under this particular 70 EV electronic beam, this fragments, whatever fragments is generated, will be same every time you do it. So that's how we can say it's a fingerprint for that particular M or whatever we're talking about. And that's what property is used when we say that we are having a library. So a library has a particular fingerprint or this fragmentation pattern which is there, and if an unknown compound goes and you generate a fragmentation pattern, that will be always same to whatever is in library, and the library matches it and says this particular fragmentation patterns matches with this compound, so this compound is probably 90%, 99% is the compound what you are looking in your separation. So, so to look at it, if you have a compound which has ABCD, which is there, different molecules, electrons goes and bombard there in ionization, you get various fragments of this particular compound, right? So the first one is you get ABCD minus, because one electron is hitting here, one electron is removed from here, so it becomes positive, and 2 electrons are moving. So that is one possible combination. And then you have, from here you can get various combinations of things, fragments which are there, which can be combination of A, B, B, C, C, D, and all that. And these combinations are ones which are going to form the fragmentation pattern for what you're looking for. So how does it look like? So your compound ABCD, which is the molecular ion precursor, which is the main precursor which was there, this is the one which will be the last peak what you see in your chromatogram. And then you have a base peak. Base peak is the peak which is the highest abundant peak in all the fragmentation pattern. It can be anywhere, not exactly here, but the highest peak what you see is called the base peak, and that is taken as 100, and others are based on that, others are computed as what is the relative abundance of those particular peaks. So that is the base peak. This is the molecular ion or precursor or parent ion, and then you have various products which we saw can be broken down, and depending on M/Z ratio and abundance, they can be really separated on this particular chromatogram what you're seeing. And like I said, it will be signature for any particular compound which is this. It will have the same signature, and you can find out what your known compound is all about. So all this is analyzed by the mass analyzer. So you have various mass analyzers which are there in the mass spec. You have quadrupole, which we talked about. It consists of 2 sets of opposite rods. They analyze mass using combination of RF and DC module modulation, and then provides nominal mass resolution. You have ion trap, where ions can be stored for subsequent analysis, and hence it's called ion trap. You can have triple stage quadrupole, which is combination of quadrupole with ion trap. You have time of flight, which depends on how far the time takes to into the flight tube by the ions to move up. And then you have magnetic sector, and then you have others like orbit trap and stuff like that. So these are various analyzers which are used in the mass spec to analyze the mass which is there. What we have is a quadrupole mass analyzer with us, and like I said, there are 4 rods which are there, and opposite rods will have opposite charges. And if the ion source, the ions are moving here in various axes, you can see x, y, z. So z axis when they move here, they move through this whatever RFDC charge, whatever is there, and the resonance ion, you fix a particular RFDC charge for this. The resonance ion will move in that particular charge and RF to the ion detector. Other non-resonance ion will go and they'll be diffusing on this particular whatever poles we have here. So you'll only have a particular ion, resonance ion, which will go and be detected based on what kind of RF and DC or current which you are flowing there. So then you can select that particular RFDC current and have a particular ion which is coming and detected here. So you can select that for different things, and you can have different kind of ions which are getting detected, and other ions are really they don't go and they are diffused in this particular quadrupole. So this is how you do. So GC flow which is coming inside, you can have it in scan mode or selected ion monitoring mode. It's called SIM. You will come across this term many times, right? And we saw what is resonance ion, non-resonance ion we saw. So scan mode is where you are increasing the voltage. When I said that you're going to change the voltage here, you are slowly increasing the voltage from here to here. So then when you increase the voltage, then you'll have different resonance ions will be coming at a particular voltage, and that's where you'll get the spectra of different fragments which are coming out and the mass being analyzed. But if you go for a SIM with a selected ion monitoring, you are monitoring only one particular ion, then the constant voltage is given across time, and then you will only see that particular ion which you are trying to see will come out. So these are the 2 different ways in which you can really see what kind of ions are coming out. So one more thing about you can have single quadrupole, that whatever quadrupole we saw can be single or can be multiple or triple, right? So here it's saying a single quadrupole, you have ion source which is doing, ion transfer optic is there, quadrupole is here, and detector is there. But you can have a triple quadrupole, GC, MS, MS. So from GC things are coming here. You have one quadrupole here which will be doing the separation. Then you have a second quadrupole which is called collision shell, which is going to concentrate thing, and then again the ions goes to the third quadrupole and then it is detected. So what we have here with us is this triple quadrupole GC, MS in our machine. Why do we have these 2 kind of things? Single one is for routine work, if you're just trying to do some simple work which you are not really interested in very high complex things. But then if you have triple quad, you can have more sensitive analysis and trace elements can be analyzed. Sensitivity is moderate here. Here very high and low noise is there. Selectivity is moderate. Extreme selectivity, you can have different modes to really do the analysis. Cons, pros are there. Complexity easier to maintain and operate, require more methods to develop, and this is cheaper, and this is a significant investment what you have to do, right? So this is all about the GC-MS part and how it works and how things are. Applications are varied and it can be used in different ways, right from oil, gas, chemicals, different gases and hydrocarbons can be analyzed. You can do environmental testing, volatile environment pollutants can be analyzed using GC-MS. Forensic toxicology, different drug analysis, steroid analysis can be done here. Food and beverages, people do use a lot of GC-MS methods to analyze pesticides, additive, contaminants. Pharmaceutical drugs, impurities, residual solvents from your processes, are they there or not? GC can be used for that because solvents are volatile in nature. Flavor and fragrances, wines, perfumery, coffee, most of this applications can be used using the GC-MS, right? So I think now it is clear how things are, what the equipment is, what different parts are, what their use utilities are, and what their principles and stuff like that are. And it will be more apt and appropriate once you go and see the system there. You can relate what we've talked about, and then you can have more questions there, right? So this is the GCMS system what we have with us, which we are going to demonstrate you today. Okay? Thank you so much for your attention. Any questions? Quick questions here? Yes, sir.
Sir, coming to the troubleshooting part.
Yeah.
As you said previously, that detectors are going to give the peaks, and we are going to determine the quantification using the linear curve graphs, right?
Yes.
So if we are getting the peaks with different, temperatures, that means if the column oven is not thermally regulated, we will get a peak that is discattered peak.
Yes.
So before, if our sample concentration is lesser, if a sample is so critical, and we cannot waste the sample. So in that case, before getting the irregular pattern, how do we rule out that if the column is thermally regulated or not?
So, I mean, thermal regulation, generally now people don't use isothermal analysis, right? You don't keep a temperature constant and do it. Because now, earlier it used to be the case where the temperature regulation was not that evolved. So people used to try saying, I'll run at 70, I'll run at 80, I'll run at 90 and see. But now that you have a gradient which you can be done, so initially itself you start with the gradient, you try to see that your column can withstand so much of temperature till, let's say, 280, 300, and you can set the temperature in your column oven also. So you slowly make a gradient which can be within a time frame which you are looking for. You just make a gradient from beginning to end towards the end of the whatever tolerance limit of your column is there, and then you do that. There you will see how the separation is. Most of the time it will be separated. Only thing is, at the times the peaks may be overlapping, so you might have to do a second run where you're trying to increase the gradient so that the peaks are separated. So now it is, most of the times you try to make sure that you are running a gradient so that there is better separation of the peaks.
And what are the important steps that to be considered while preparing the sample?
Sample preparation is depends, like what is your compound which you're trying to. I mean, you will know the class of compound. Either it's a lipid, it's a carbohydrates, it's whatever compounds are there with you, alkaloids or secondary metabolites. Based on that, you have some functional groups on that. You can modify those functional group with derivatization, and derivatize that so that they can become more gaseous in nature or volatile in nature. So that kind of protocol you'll have to make. So there are various protocols for that, maybe methyl ester formation, cellulation formation, and those can be used and make the samples from that and derivatize it.
Okay, and what are the key quality attributes that we have to look at?
In terms of?
In terms of sample preparation or in terms of...
So the sample, like when we say it's very sensitive technique, and so you have to make sure that your samples are relatively clean and pure, right? They don't have anything which will interfere with the analysis, or there are no particle matter which are there, right? So your extraction methods should be such that all these things are taken care of before injecting the sample in the GC, and try to see that it's not very highly concentrated. The concentrations are less. So because like we saw, the sensitivity of GC is in terms of even nanograms and picograms. So you have to, if you load too much of sample, then your column will be clogged and you'll have column bleeding and problems like that.
Thank you.
Yeah, thanks. Okay, thank you.
Thank you, sir, for this meaningful lecture. Now it's time for HPLC lecture, and it will be delivered by Professor Santosh Kumar Pati from the Department of Biochemistry. Thank you, sir.
What we are going to discuss today, or what we are going to learn today, is about what for HPLC and how HPLC looks like, what are the major components, what are the general principles of HPLC analysis, and then an in-depth study about the different parameters, and then finally we'll see what we have learned today. So to begin with, what for HPLC, basically like any other chromatography, HPLC actually does analysis of a mixture of compounds. When we say analysis of a mixture of compounds, it sounds pretty simple, but you are going to really, see a variety of applications as we move on, you will realize actually. In addition to analysis, there are also ways to separate something called preparative HPLC, where you can also separate the components, the mixture of the compounds. In addition to this, HPLC can also be used to analyze optically pure compounds. These compounds are also called chiral compounds, and they have a lot of importance, especially in the pharmaceutical sectors or in the medicinal chemistry or in the pharma sector. Feel free to interrupt me whenever you have some doubt actually. Now the second thing is, what for HPLC? What are the applications really? There are a number of applications. I have just tried to give a glimpse of it, some of these things. For example, you have a metabolite profiling in metabolomics actually, to detect and quantify small molecules or small metabolites such as amino acids, organic acids, sugar, or any metabolites that can be analyzed using HPLC. Drug metabolism studies, for example, to identify and quantify drugs and their metabolites in the biological systems or fluids like blood, plasma, and urine. This can be easily analyzed by HPLC. Hormones can be analyzed, for instance, to accurately measure the hormones such as steroids, catecholamines, thyroid hormones, and many other small molecules present in several biological samples can be easily analyzed by HPLC. To detect biomolecules in clinical diagnostics, for example, detection of biomarkers associated with, say, disease, or including vitamins, lipids, or any other clinical relevant compounds, they can be analyzed by HPLC. Coming to enzyme experiments pertaining or using enzymes to monitor enzymatic reactions, say enzymatic assay or enzymatic kinetics, enzymatic inhibitions, to separate the substrates, to quantify the substrates, to quantify the products and the intermediates. For most of these things, HPLC can be widely used. Purification of natural products to identify biologically active compounds from plants, microbes, or marine organisms. If you have certain compound, that can be analyzed by HPLC. Food and nutritional biology research to analyze vitamins, antioxidants, any other like nutritional components in foods and biological samples. For quality control, HPLC is exclusively used actually for a number of purposes, especially in biotechnology and biopharmaceuticals, to check the purity of the compound, to check the stability of the compound, and consistency of the biological derived drugs such as monoclonal antibodies, vaccines can be monitored or can be analyzed by HPLC. Proteins, nucleic acids. So as you can see here, there are a large number of applications. It ranges actually from, say, metabolites to several other sectors. Now, how this technology is different from other chromatography techniques? Well, in any chromatography techniques, there are two things. One is a mobile phase, another is stationary phase. Like you heard about GCMS, where the mobile phase and the mobile phase is actually gas used to carry things actually. Here it's a liquid chromatography, therefore the mobile phase is actually liquid. And the stationary phase is solid actually, mainly there are some chemical coatings. We will discuss about the stationary phase very soon. It detects a wide range of components starting from high molecular weight, polar, non-volatile, biochemicals, drugs, metabolites, as I discussed in the previous slide. Now the beauty is power of the mobile phase for higher resolution. As the name suggests, high performance liquid chromatography, liquid is the mobile phase, and a variety of liquids can be used, a variety of solvents are used actually, and that actually provides is really the power of HPLC, where it can resolve a number of components. Unlike GC or GCMS, this is a non-destructive technology. At the end of the analysis, if you want, you can retain your compound actually. On whatever you analyzed, you can isolate it or you can take it out actually. Whereas in case of GC or GCMS, the sample is actually burned. And this is analyzed at room temperature. Lower detection limit. nanomoles or picomolar level, nanomoles or picomoles of compound can be detected. How the HPLC looks like. Earlier it used to be something like on the right side you have different like compartments. One is for the pumps, another is for detector, injector. But there are today what we are going to visualize today is actually the one on the left side. This is from waters, and this is what you are going to be demonstrated. You can just see everything is in one box. It's very compact, and that's how it looks like actually. So this is a modern day HPLC, I would say. Yeah. Now let us try to understand how the HPLC works. This is a schematic representation of how the HPLC works. You have mobile phase. By now we know that this HPLC, high performance liquid chromatography. So liquid is the mobile phase. So you start with the liquid. You have the mobile phase liquid actually. And then the liquid is actually pumped because there is a pump which actually at the high pressure, the liquid is pumped, right? So then the liquid is carried by the pump, and then there is injector. Now the liquid which is pumped by the pump is actually coming through the HPLC, and you inject your sample. This sample actually could be a mixture of compounds, could be a single component, depending on whatever the nature of the component. Now, all these components, let us say there are 3 components, they actually pass through the, you have the column which is present the vertically, and you can see, let us say these components are passing through the column. The column, we are also going to discuss in detail about the column. The particle diameters could range from say 1.5 to 10 micrometer. Then the components reach the detector. When they reach the detector is going to analyze. The detector could be, here I have just said that there is a flow cell and there is UV light is passing through this. And as you can see from the left to right, as the flow is, the column is, the liquid carrying the components are flowing through the column, then it is going to pass through the flow cell. And the flow cell, you have the UV detector, or there are different detectors which we will be discussing soon. And the detector is going to detect. Then the liquid is actually coming, which you can collect as the waste. So the detector is attached to a computer, and it is going to detect. You are going to have a chromatography. There is a chromatographic data system. Let us see how it looks like. So there could be, in the previous slide you saw there is a single mobile phase, but you could also vary. There could be more than one mobile phase. You can have mobile phase A, mobile phase B, which means you can take 2 different solvents. And then these different solvents are actually first, they have to go through a vacuum degasser. This vacuum degasser is something which actually degasses, or there should not be any air bubbles, because that is going to cause trouble. And then after this vacuum degasser, these components actually pass through the mobile phase, mixing. Then they mix at a certain ratio, whatever you define. And then this mixed mobile phase actually reaches the pump. Its pump is throwing them, and they are passing through the injector. At the injector, let us say you have 3 components. You have a mixture which basically consists of 3 components, say yellow, green, and the pink or cyan. Now these components actually you have injected. They come to the column. This is the beginning of the column. And then as they move on, let us say you can see the pink one is coming first. That means the pink one is actually has gone through the column fast actually. That means it is having less interaction, and therefore because the pink one is coming out of the column fast, it is reaching the detector first, you see the first chromatogram, the pink one actually. And then the yellow one is reaching the detector, you get the yellow chromatogram, and then the green one comes, you get the green peak in the liquid chromatogram. So this is how typically you see a chromatogram in the HPLC chromatograph. Let's now talk about the HPLC, how it functions actually, and a little bit about the columns actually. So the individual components of the sample are now moved down by the PEC tube. This PEC tube is nothing but your column. Column with a liquid, or the mobile phase. Actually this mobile phase is which is forcing them through the column by high pressure. That's how it is high pressure liquid chromatography, and they are delivered by the pump. What you see on the top of the figure, it's something like you can see there are some mechanism called adsorption, desorption, which means the green part is the support. This is your the column, and then you have 2 circles actually. So let us say we are talking about protein, or it could be any other analyte. So there is a red protein, and there is another analyte actually in gray. And all these analytes are, as they are passing through the column, they are also mixing with the solvent, therefore they are solvated. So they try to interact with the column, right? So there is some sort of adsorption, and also they try to move forward, therefore there is a desorption actually. So there is adsorption, desorption, and this is what is going to happen. This is what is happening while these components pass through the column, right? These components are separated from one another by the column packing that involves various chemical and physical interactions. So there are not just physical interactions, as I said, like adsorption or desorption, there are also chemical interactions as well. You will visualize as we move on. For example, in the second case, the second figure shows actually this is a typical column. The top one and the bottom one, you can see after 10 minutes, the analytes are moving, and you can see that these analytes, they interact differently. They interact differently depending on the chemical nature of their component actually. Separated components are detected at the exit of the tube by a flow-through device or detector that measures their amount, and an output from the detector is called liquid chromatograph. So basically you get a liquid chromatograph. As these molecules, they reach the, from the column, there is the detector actually detects, then you get a chromatographic peak actually. Like the case of GCMS, here also you have two different modes. One is called isochromatic, another is gradient elution. In case of isochromatic, as the name suggests, actually the isochromatic elution where the mobile phase composition is it's a constant. That means, say, for example, a certain ratio of these components, maybe 1 or 2 mobile phase, but a certain ratio is fixed throughout the analysis actually. So that's called actually isochromatic, which means the mobile phase composition is kept constant throughout the run. So in that case, if you look at this graph, actually the red one is representing the isochromatic, which means with increase in time, you can see the mobile phase composition remains constant. The other one, the blue one, is actually called gradient, not necessarily a linear one actually, it can be different. It's something like, so gradient basically means, okay, before I go to gradient, the isochromatic is best used for simple separations, and it's often used in quality control analysis. For example, you have say paracetamol. Every company is producing paracetamol actually. Each time they are producing, say, several batches. Each time they have a program, you just inject it, and this program is fixed actually. The isochromatic grading, isochromatic program is fixed. You just have the sample and then inject it. You are going to see that the sample purity can be analyzed actually. Whereas if you have a new sample and you don't know how to, what program it runs actually, how these components are separated, you can try with your gradient elution. Gradient elution is basically something where you can play around with the mobile phase composition. This is altered periodically. You can say that for first 5 minutes, I want to have this composition. Let us say the two mobile phases are A and B. For example, hexane, isopropanol, or water, acetonitrile. You can say water could be 60%, acetonitrile could be 40% for first 5 minutes. Another 5 minutes could be 70-30, another 5 minutes could be 80-20. You can play around actually depending on the nature of the compound, and so that you can get good separation actually. So this is kind of usually done for method development or for new kind of compounds actually. That's where it says that this is best for analysis of complex samples, and this is often used for method development for unknown mixture. How these HPLC columns look like. HPLC columns could be mainly of actually two types, analytical and preparative. Mostly this talk is focused on analytical actually, but there are preparative HPLC is also possible actually. Well, this analytical HPLC columns, they look like this. As you can see there, they are the internal diameters of something like 1 to 4.6 mm, and the length is about 15 to 25 cm actually. Preparative HPLCs also have something like more than 4.6 millimeter diameter, little wide, and the length could run from 52 to 50 mm. HPLC is broadly used for 4 major types of separation, or 4 modes of separation actually. Number 1 is reverse phase chromatography. Second is normal phase chromatography. Third, fourth, I have we are not discussing actually ion exchange chromatography, size exclusion chromatography, which work typically in the principle of HPLC, but per se because there are, for example, ion exchange and size exclusion are run by FPLC. So FPLC and HPLC are on the same principle, but I have not included them for this topic actually, for this seminar or this lecture actually. So we'll be basically talking about reverse phase chromatography and normal phase chromatography as we move on. There are another few columns are shown at the bottom actually. You can see them like they are in golden color actually. These are typically chiral columns actually. I have also mentioned this few slides back that this molecule HPLC is also used to analyze chiral molecules or optically pure compounds. Basically, the composition or the internal composition of these columns are different actually. As we move on, you may notice some of these things. Yeah. So let's talk about reverse phase chromatography, or RPC basically. Here the column packing is mostly non-polar. And this, when you say non-polar, this is like C18 or C8. Basically C8 means 18 carbon or 8 carbon chains actually, or phenyl. So that clearly shows that these are actually non-polar in nature actually. And the mobile phase is water. So keep it in mind that the column is non-polar and the mobile phase is polar actually. The mobile phase could be like buffer or water, or it could be some sort of miscible organic solvents. When I say miscible organic solvents, the organic solvents which are miscible with water or buffer, basically kind of acetonitrile or methanol. These are the common solvents which are used. RPC, or reverse phase chromatography, is by far the most popular mode. More than 90% of the time when somebody is using HPLC, they are using actually RPC, or the reverse phase chromatography. This technique can be used for nonpolar, polar, ionizable, ionic compounds, making RPC a really versatile method for analysis of different compounds actually. One begins with a predominantly water-based mobile phase. For example, you may ask actually how to decide the mobile phase. You can start with predominantly water-based. You will also realize as we move on actually after a couple of slides, I will give a little bit more about this. One begins with predominantly say water-based mobile phase, and then you can start adding organic phase as the function of time actually. The organic solvents actually increases the solvent strength and elutes the compounds that are strongly retained in the RPC packing. How this compound is retained or eluted, that will be realized actually soon, very soon I will be talking about. Composition of stationary phase. Now, when we are saying composition of stationary phase, we are talking about the stationary phase, that is column actually. The column basically made up of siloxane actually. As you can see, it's a kind of ether of silicon, oxygen. So this is your siloxane, silicon, oxygen, and alkane. Any chemical compound is basically composed of these units like R2SiO. R is something, R is a hydrogen, or it could be hydrocarbon. Last slide I told you actually it could be like C8 or C18, right? So you can see, for example, branched or unbranched backbone of alternating silicon or oxygen atoms like SiO with side chains R are attached to the silicon atom. That's how the column is composed of actually. In commercially reverse phase packing, the R is actually siloxane structure with a C18 chain, which is called N-octyl, or it could be C18. These are actually popularly used. And the longer alkyl chain produces packing that are more retentive and permit the use of larger sample. Why it is more retentive, you will realize very soon actually. So typically shown actually C8 or C18, which is also called as octyl silyl or octadecyl silyl, SiCH2 7CH3, or silicon is attached to 8 carbon or 18 carbon chain actually. Now this is a important slide actually, normal phase chromatography. In case of normal phase chromatography, the next one is actually more important. Here I'm just comparing the reverse phase and the normal phase. Normal phase chromatography is just opposite of the reverse phase. In case of reverse phase, we said that the stationary phase is non-polar and the solvent is actually polar. Here the column packing is actually polar, which means the silica gel is attached to something like cyanopropyl bonded or amino bonded. Therefore, the column is actually, the stationary phase is polar, and the mobile phase is usually non-polar, something like hexane, isooctane, something like this. And the normal phase separations are performed in less than 10% of time. Kind of, I said 90% in the previous case actually. This technique is useful for water sensitive compounds, therefore you use less water here. Basically, we are using hexane, isooctane, this kind of solvents. Geometric isomers, a class of compounds like lipids or something like that, or also for chiral compounds, which are mostly used in the pharmaceutical sectors. The R group of this siloxane, the structure that you have seen in the previous slide, is polar here. The functional group is attached something like cyano, like C2H4CN, or diol, or amino, diethylamino. All these structures clearly signifies that polar entities are attached actually, and this makes actually the column more polar. Now this is an important slide actually. Basically, we need to understand how these molecules are separated actually. So this is a normal phase versus reverse phase chromatography. So by now it's clear that a normal phase chromatography has polar stationary phase and non-polar mobile phase. For a reverse phase chromatography, the stationary phase is non-polar and the mobile phase is polar. All right. Now look at the chromatogram. So the concept is like this. Let us say, let us focus on the left part of the figure actually, normal phase chromatography. Well, in case of normal phase chromatography, I repeat, the stationary phase is polar. Stationary phase means the column is polar actually. So if the column is made up of polar components, then the polar compound, so if I am going to analyze a mixture of molecules and this mixture of molecules have maybe have different polarity, the polar molecule will find more interaction with the polar component of the stationary phase. Because the stationary phase is polar, therefore polar components will find more interaction. Because polar components will find more interaction with the stationary phase, they will be retained because it is talking, like I am talking to you actually. Some time is spent. Similarly, these molecules, they will be interacting with the stationary phase, therefore they are retained actually. Therefore, the non-polar ones will be moved out. So the non-polar ones will come first actually. As you can see here now, the order of the solute polarities, if you see, A is more polar, then B, then C. So C comes first actually. You can see there, C comes first, then comes B, then comes A. C comes first means C is actually non-polar because it is not interacting. Therefore, it comes out first. Then comes B, then comes A because A is more polar. A is more polar. A interacts more. Therefore, A is spending more time. It comes at the end. Clear? Now, same thing or a very similar thing on the other side actually, reverse phase chromatography. In case of reverse phase chromatography, the stationary phase is non-polar. Because the stationary phase is non-polar, non-polar compounds will have more interaction. Therefore, non-polar components will come late. Polar compounds will not interact actually because the stationary phase is non-polar. Therefore, they will come first. So, in that case, A is coming first, which is more polar. You can see the solute polarity, A is more than B, more than C. So, because A is more polar, it is not finding interaction, it comes first. Clear? Then comes the second half of the picture actually. What happens if you increase the polarity of the solvent? Well, in the first case actually, we are saying that the stationary phase is polar. Stationary phase is polar and your components are finding actually interaction, right? So if you increase so here the mobile phase is actually non-polar. Because non-polar, they are actually coming, they are actually separated easily. The moment you increase the polarity of the solvent, this polarity of the solvent will also try to pull these analytes. These analytes which are polar actually, they will also be pulled fast. Because they are pulled fast, therefore the resolution is less. You can see in the top case, the resolution A, B, C are separated. Here you increase the polarity because the solvent is now more polar. Therefore, they also try to pull those molecules actually. So these molecules will find now less interaction with the stationary phase. Therefore, they are coming close actually. It happens on the other side. If you look at the non-polar in the reverse phase chromatography, when you the medium polarity is actually so in that case actually high polarity is the mobile phase. If mobile phase is highly polar, it is not going to interact because the interaction is between non-polar solute and non-polar the non-polar analyte and the non-polar stationary phase. So the more the polarity of the solvent, the less interaction it finds. The moment you decrease the polarity of the solvent, right, that the resolution is less. So this is basically the concept which is actually used in case of HPLC. Yeah, is this clear to you or okay? This is a typical actually analysis of how about the polarity of the mobile phase and the polarity of the analytes. Analytes, the polarity is basically hydrocarbons. They are less polar than ethers, esters, ketones, and aldehydes, amines, and alcohols. This is something you have to keep in mind before you analyze actually the type of compounds, because based on that you can expect actually how the kind of separation would be. And mobile phase, because mobile phase is something important in this case, it plays crucial role actually. The selection of mobile phase is also very important. You should have a strong idea about the solvent polarity actually. So for example, your hexane is non-polar, THF and acetonitrile water and alcohol water. So that side is more polar, this side is non-polar, and the same thing is visualized here. Yeah. This is the polarity of the analytes and mobiles in stationary phase. We are talking about the stationary phase here. You can see that is starting from silica, then CN, C8 and C18. C18 is more non-polar, C8 is less non-polar, then CN and silica, that is actually towards the polar part actually. So the same thing I don't want to repeat. We are already familiar with the non-polar and reverse phase chromatography and their composition. typically the same thing, reverse phase, nonpolar retained. Actually, it's as you can see here, we have already analyzed this thing, therefore I'm not spending time here. Same thing actually, the polarity, the order of polarity is already discussed. So whatever I've discussed so far can be summarized here. Actually, you can see the stationary phase. If the stationary phase is polar, in case of normal phase, mobile phase is non-polar, elution order is most non-polar comes first. And then when you increase the solvent polarity, there is a reduction of the retention time actually. Interaction is based on the hydrogen bonding, dipole interactions. In case of reverse phase chromatography, your stationary phase is non-polar, mobile phase is polar, elution order is most polar comes first. And as you increase the solvent polarity, there is an increase in the retention type. Here the interactions are based on hydrophobic interactions. All right. Does temperature has any role to play in this case? Yes. Reproducibility. For example, the retention time of the peaks in HPLC is actually temperature dependent. Why? Well, you see, if temperature varies, then it's difficult to assign the peaks to the specific compounds in the chromatograph, and the peak areas and the heights also may vary. Why? Because actually the moment you increase the temperature, there is a decrease in the mobile phase viscosity, right? As the viscosity changes, the pressure is actually changed. As the pressure is changed, it allows the higher flow rate, and therefore everything actually changes, right? So all of them are actually interrelated. Solubility. Yes, temperature also plays an important role because you have to analyze some analytes, and the solubility of these analytes is very important. Certain chemical compounds may have low solubility in the HPLC mobile phase, and therefore they have to be injected with the flow stream when they are and they may precipitate actually if you play around with the temperature. Stability, it also depends whether the compound is stable or not. For instance, if you are talking about some biomolecules like proteins and all, temperature also plays an important role here. Detector, like you have seen in the case of GCMS, detectors also play a very important role. There are a variety of detectors available, but for simplicity, I am presenting 4 of them here: photodiode or UV visible absorption detectors, differential RID, it's called refractive index detector, fluorescence detector, and mass spectrometer. So what is UV visible spectrometer, or the spectroscopic detection of ultraviolet absorption? An ultraviolet light beam is basically, so in this case the detector is actually a UV based detector, and here the UV beam is actually directed through a flow cell. The flow cell picture I have shown in previously, right? And a sensor actually measures the light which is passing through the cell. You are all familiar with the Beer-Lambert's law. So whenever a beam of light comes, something is certain concentration is actually absorbed, and whatever is absorbed, you are basically trying to analyze that. There are diodes which are present there, and from there you are going to it is going to convert that into some sort of electronic signals, and those are actually basically detected in the HPLC. So if a compound actually elutes from the column that absorbs the light energy, it will change the amount of light energy falling on the sensor, just now I said, and the resulting change is then converted into some sort of electric signal, which is amplified, and that is detected in the recorder actually. A UV spectrum is sometimes also obtained, which may aid in the identification of a compound or a series of compound. Now the limitation of this is actually the compound should have some sort of UV chromophore, then only you can detect it actually. Now in contrast to the previous one, actually this RID, or the so-called refractive index detector, which is also called as universal detector, actually compounds which do not have UV moieties or UV detectant groups which can detect UV, they can be analyzed by RID. So the ability of the compound or the solvent to deflect light provides a way to detect it. In this case, actually, light is passing and then light is falling and it is actually deflected. The RI is a measure of the molecule's ability to deflect light in the flowing mobile phase in a flow cell, and this is basically relative to the static mobile phase. So you have a mobile phase, and which is without any component or without any analyte, and in comparison to that you have another mobile phase where mobile phase is with the analyte actually. So there is a comparison between these two, and then you can find out the relative static, you can find the relative deflection of light between these two. That gives you the detection actually. So the amount of detection is actually proportional to the concentration. Higher is the concentration of your analyte, higher is the detection. The RI detector is considered as the universal detector, but again it has some limitation. It is not very sensitive. This is ideal for detecting non-UV observing compounds like sugars, alcohols, or polymers. Then comes fluorescence detection. So this is actually mostly used for comparison to compared to the UV visual detector. Fluorescence detectors are often sensitive, higher sensitivity. They have higher sensitivity, and the selectivity actually that allows to quantify and identify compounds and impurities in complex matrices at extremely low concentration. So they are actually more sensitive. Even at very low concentration, they can be detected, provided the analytes are fluorescent in nature actually. Then comes mass. When mass is attached to this machine is called LCMS, but what we are going to detect today, we are going to demonstrate today is actually HPLC, where mostly PDA or photodiode array, or basically UV is the PDA is actually the broad way of saying this. So PDA is the detector actually. In case MS is attached to the HPLC, it is called LCMS, and it is Professor Ajay has given a thorough lecture on MS, so I'm not spending a little time on this. Like he said, actually the sensitivity is very high. It is actually a fingerprint, and it gives unique to every compound. Actually, the detailed thing he has already described, so I'm just skipping this actually. Few things to keep in mind in case of HPLC. For example, these are the measurable parameters in HPLC. Partition coefficient. Partition coefficient, for example, you are analyzing an analyte, and this analyte is carried by a solvent actually. So basically, you have to see what is the solubility of this compound, or what is the concentration of the compound in the liquid phase versus the solid or the stationary phase. So that is decided by the partition coefficient. This is very important also, because the concentration ratio of the analyte in the liquid versus the stationary phase should be constant throughout the concentration. You take 1 millimolar, 1 picomolar, or 1 micromolar, this ratio has to be constant actually. There is something called capacity or retention factor. Capacity or retention factor is something, a parameter which compares the relative rate of the solute migration along the column. For example, you can see here the capacity factor K prime is for a solute is calculated like K prime is equal to TR minus TM by TM, where TR is the retention time of the peak of interest and TM is the unretained peak of retention time. What does that mean? That means, for example, you are analyzing something, and there is something called solvent peak. Sometimes it just comes actually. So without any component, without any analyte, the solvent takes some time to come actually. That is your TM. On unretained peak, when the peak is not, when the compound is not retained, it is just coming out actually, it takes some time actually. In this case, let us say this is your TM, and TR is the retention time of the peak actually. So your K prime is calculated like TR minus TM by TM. Ideally, it should be something like 5 to 7 actually. If it is less, that means actually it is very close to the solvent peak, and therefore that is not a good separation. The selectivity or separation factor. If you have more than one peak, how these peaks are separated actually. So these are separated, the peak separation is also calculated by or measured by something called separation factor. This is basically a relative position of the two peaks actually. So the selectivity factor alpha for the two solutes is nothing but the ratio of the larger capacity factor K prime B by K prime A. K prime B and K prime A are the capacity factors of B and A. The capacity factors are something which I just now discussed in the previous slide actually. So in this case, you can see here actually your for the two peaks, and then your KB prime by KA prime is your alpha. Peak resolution is defined by RS or resolution factor. This is called RS is equal to TR2 minus TR1 by W2 plus W1 by 2, which means the 2 goes to the numerator actually. 2 times TR2 minus TR1 by W2 plus W1, where your TR is nothing but the retention time of the second peak, TR1 is retention time of the first peak. So basically you see that how these two peaks are separated, TR2 minus TR1 by W2 minus W21. W1 and W2 are the width of these two peaks. So the narrow it is actually, or if they are, if less the W1 and W2, better is the resolution actually. These are some of the typical HPLC chromatographs, like you heard in the case of GCMS. HPLC is also used in several sectors, starting from pharma sector to flavor and fragrance, in analyzing the pesticides. In multiple sectors it is used actually. And this is a typical chromatogram of which is analyzed at C18 column, as you can see here. And the difference is this is done in the reverse phase chromatography. You can see C18 column, and the order of elution is actually just changed when the same thing is analyzed in a polar phase chromatography. This is again a couple of pictures of chromatograms, typically how they look like. You can see clearly that like 16 components could be easily separated in HPLC. So what we'll learn today is actually basically the advantages of HPLC over other chromatographic techniques, the importance of the several components of HPLC, the fundamental principles of HPLC, and the major separation methods, modes basically we studied, the important parameters we studied actually for the analysis of a mixture of components, factors affecting the parameters, type of detectors, and the important measurable parameters at the end. Application we didn't touch really too much. So with this I finish HPLC, and I would be